Okay, so I guess we'll get started. And today I want to talk about panoramic imaging, like in virtual reality. We often have virtual reality headsets where we do a VR capture of something, and you can sort of see inside that virtual space. And how do we build those virtual environment maps? So many of you probably have a VR headset already, or you can view it online. There's a VR viewer. And so we often look at how do we combine multiple images together to create an environment map so that you can explore remotely into a space. And when we try to combine these images, there'll be a simple law of composition. And so what we're going to do, I'll share my screen just to look at a couple of examples of what. See, I'll share this screen. So we'll start by seeing some video feedback. And then if I look at VideoOrbits, so when we're doing design of a space or a building or a facility, we often want to create an environment map or a VR map. So when we're doing renovations to a facility, for example, in building design, this is a virtual environment map, and you can explore this in virtual reality. And so we can look around the room and see where the fixtures are installed. And then if there's heating and ventilation and chilled water pumps and things like that, we can explore into the mechanical room and navigate around. And one of our members of SwimOP has this building automation system where he scans virtual reality environment map. It just takes a whole bunch of pictures of the building, and then you can design and lay out facilities in the building. So typical panorama looks like that top image, for example. That's a 360-degree environment map. A common characteristic of these 360-degree environment maps, you'll notice them. One thing is you have sometimes the same things in the picture twice. This is a selfie, 360 degrees, and you can see I'm in the picture twice, once at the left side and once at the right side. And in that sense, it's a full 360 degrees view, 360 degrees, 2 pi or teth, 1 teth. And so when we look at those environment maps, these are some examples of panoramas. So another feature is you often have people in the image more than once because they move around. So here you see, this is Dan Bowman. He appears here, the second time over here, third time over here. And so what happened as the camera was going around scanning that scene, people were just having a little bit of fun playing with it. And that's an old tradition from the days of the MIT freshman photos, which are usually taken on a panoramic circuit camera that was made in 1904. This camera has a film strip in it, and it turns around and scans the whole scene. And that's kind of how we often build these VR maps. And of course, we can have fun with them by overrunning them. And so that's what I call a type 1 panorama. Here's a skyline of Toronto that was composed of many pictures taken of the same subject matter. So what has been done here is multiple pictures of the same subject matter have been combined together under a simple law of composition using algebraic projective geometry to make this sort of wide field of view and high resolution. So the pixel count of that image, it's about 22,904 pixel across by 5,276 high. So it's got a fairly high resolution. And of course, we can go into gigapixel regions with the resolution of these things. Here's a picture of West Island, and you can see the full 360-degree view of the Ontario Place West Island there. And if we view it in an environment viewer, of course, if you look at virtual reality, it feels like you're there because you're exploring or navigating around the space. And so we call this is sort of a typical sort of beach view. So we build that, we call this a type 1 panorama. And of course, this is horizontal. It's of course fun and interesting if you go vertically. There's a vertical panorama. Normally we go horizontally. There's the island there. And this is the view from my roof. Now what's interesting here is there's streetcars going by, and one streetcar is going west and the other streetcar is going east. And the eastbound streetcar appears as if it's foreshortened, it's contracted. And the westbound streetcar is lengthened or dilated because it's going with the flow of the camera. The camera is scanning from left to right in this case. And so the one streetcar is dilated and the other is contracted. So this is just interesting to observe or note properties of this imaging modality. So these, what I've shown so far, are examples of what we call type 1 panoramas. And the other way of stitching images is what we call type 2, and that occurs when the subject matter is flat or planar. So in this case, we have relative motion between the subject matter that's being imaged and the camera. And either the camera moves along the subject matter or the subject matter moves along the camera. Here, the camera was stationary with respect to the Earth, and the streetcar was moving with respect to the Earth. And this is a consolidation of multiple images as the streetcar moves, and thus we have an accurate portrayal of subject matter on the plane of the streetcar, on this flat planar surface. And over a certain region in the middle of this image, it's a type, what we call a type 2 panorama. And then towards the right, it goes back to being what we call a type 1 panorama. So I call this a type 3 panorama because it's a mixture of type 1 and type 2. And here's another example. In the middle, this is a type 2 panorama, and at the left and right edges, it's a type 1 panorama. That is to say, it's panning. So what I did is I panned the camera until the streetcar started coming, and then I let it rest, and then I continued panning. And so in this case, it's a consolidation of multiple images that reports on a rigid planar patch in the middle. Roughly, the streetcar is approximately a planar flat surface. And then in this way, it's the planar surface is imaged. Here's another example of, this is a purely type 2 panorama. And so I call that a type 2 panorama. And what I would do is just annotating these. And that is a good example of, you can see the flat surfaces. The buildings that are flat surfaces are reproduced faithfully to some degree, but things out of that plane are not captured in a true and accurate way. Here's another interesting example. One streetcar going one way is foreshortened and the other streetcar going in the opposite direction is dilated. So now as we look at this concept is called VideoOrbits. And this is something that I invented back in the 1980s, published in the 1990s, compositing multiple images of the same subject matter. And so here's an example. There are 3 pictures there, and they're related to one another by simple algebraic projective geometry. There's a wide shot that captures the whole scene, 2 wide shots actually that are overlapped to increase the field of view. And then as we zoom in, we may capture some subject matter at greater resolution. And so there's a relationship between the images. There is the original image here, and there's affine coordinate transformations, projective coordinate transformations, and so on. And we'll talk about those. Angle shot from my eyeglass. And in this picture, we have a number of images that are stitched together based on this simple law of composition using VideoOrbits. And then there's the original code for that. So this is wearcam.org/orbits. Here's a gallery of images. This is a simple example of 3 images that are consolidated. And you can see there the laws of algebraic projective geometry are simply followed in combining or consolidating those images. This is my ITAP view when I'm at the bank. And so this helps me remember, using the wearable face recognizer, that this is the person I talked to last time. Or actually, I remember the person over on the other side was someone I was talking to. And this is a message coming in from someone else who's looking through my eyeglass and reminding me to talk to someone at the bank. And so this is an environment map. As I look around, it builds an environment map. I call this painting with looks, look painting. And as we look at the world around us, we see what's happening. This is looking up and down in this case. So I'm talking on this payphone here. And as I look up, I see a surveillance camera. So this captures the sort of gaze or look. And if we look around completely, it'll capture everything that's in that view. Now I'll turn off my screen sharing, comes back to the camera. So if you can chat, I'll open the chat. Let me know if you can hear me clearly and accurately with once and only once without any disruptive echo. Can everybody hear me well? Good. And then were you able to see those shared images okay? Good. Okay, so now what I'm going to do is I'm going to switch over my view to the chalkboard. And additionally, I'm going to drop in an inset image in the upper right-hand corner there. And swing my camera over there to the chalkboard. So now you should be able to see me over here with the overhead view of the chalkboard. So I just want to kind of explain sort of how imaging works in general. So if we have a camera system, normally we might have subject matter here. Typically, we have subject matter like this, something here, and then we're going to have some kind of a camera device, which will have some kind of an imaging device. And that might be like this here, let's say. And then I'm just going to draw that in there, this wire coming up there, where the connector is a little BNC connector. And so inside that camera, there'll be an actual camera obscura, sort of as a darkened room, little room in there, if you will. And the rays of light come in through that lens and enter that little room and form the image here inside there of whatever is outside the camera. And there'll be a certain distance here, which if the camera is focused to infinity as its focal length, And of course, if the object is a little closer, the lens will be out a little further, but it might be a pinhole camera as well. And so that image gets formed. And usually when we draw things, we draw from left to right. Diagrams move from left to right and top to bottom, the way that we write. We normally write diagrams in this way. Something is here, and then something is here, something is here, and so on. And we prefer to understand and see things from left to right. Ordinarily, and the light travels from left to right in a typical diagram, just as we do. And the reason for that, of course, is because when we write letters from left to right, usually people write with their right hand on ink, and then you don't want to smear what you've just written, because you might rub it out like this. And so when ink was invented, writing started going left to right. And of course, in older languages like Chinese originally started in the upper right-hand corner and went down columns towards the left. And of course, Hebrew letters are like Aleph, Bet, Gimel, Dalet, A, Vav, Zayin, Het, Tet, and so on, Yud. And they go the other way. And the reason for that is because they were written with a hammer and chisel and in stone. And when you're writing in stone, of course, people would typically hold the chisel with their left hand and the hammer with the right hand. And then when you're writing, you don't cover up what you just wrote. So in the old world, perhaps things went from right to left, but in the modern world, things go from left to right. That's the way television screens scan and everything. So we're sort of used to drawing things in this direction. And so now, if we wanted to make that simpler, if we wanted to simplify this diagram a little bit, I could conceptualize it this way, just to simplify it. And I'm going to say there's a single point right there, which is the pinhole, the point of that pinhole, or the center of projection of that lens. That's called the COP, the center of projection. And I would simplify it that way, and then say that this is called the optical axis, the axis down the center of that lens, and perpendicular to this imaging plane. So I don't need to really draw the whole camera. I can just say that the camera is simply an optical axis like this, and an image plane that meet at right angles. And I have one point here. And I call this point the center of projection. And this is called the optical axis. And what I would say is that and I realize that the whole thing's inside a dark room called a camera, but I often don't need to draw the box around the camera. I can just simply think of it mathematically as this center of projection that then allows us to form the image like this, and then whatever's there is here. Simply. Now, if I want to simplify it further, it makes sense to think of it in the positive direction. So now, let me take and say that the film plane is here, even though it isn't. I'm going to put the film plane on the same side as the object plane, and then I'm simply going to draw my lines to here, and where they intersect is the image right here. And they're on the same side now. And in this way, this is in the positive direction. So instead of the camera being like this, what we imagine is the film plane or the image plane out in front of the camera, and rays of light come and touch it like this. And in this way, mathematically, it's a little bit simpler to envision or imagine it. So that's what we often draw. So now, if I draw in that way, I have some sort of an image plane. Now it would be interestingly simpler perhaps, to draw it in the opposite direction and let the optical axis go out this way from left to right. Let the image plane be here. This forms a right angle. And then our subject matter is over here. And instead of rays of light going into the camera, well, imagine the camera emits particles. We could call them scotons, particles of darkness instead of photons. And we can draw from left to right like this. Put the origin at the left-hand side, which is the COP, the center of projection. Let's think of that COP at the left-hand side of the image. And then let's think of the subject matter to the right. And in between, we have the image plane. And now rays of light come this way, or similarly, scotons go that way. And we can talk about valence flux as something that comes out of the camera. And if we think of it in this way as a ray tracing exercise, as we often do in computer science, we often trace rays outwards from the camera and figure out where they touch objects. And that makes it simple mathematically, because then we have this distance f is positive, and then the depth distance, which I'll call that z, call that big Z, is in the positive direction. And I can call this little z. And then the distance away from the optical axis that we have here, that's big X, let's say. And in 2 dimensions out of the page, imagine there's another dimension Y, as the image is 2-dimensional. And then in here, we have little x. And we could say, what is the relationship between big X and little x? And of course, we know the ratios are similar, that little x over big X equals little z over big Z. And so we have a very simple relationship. And then if, for example, I took a center of projection here and came out from it, and then I took some series of points out here, and let's say they were uniformly spaced. Like this. And they would form an image of points also uniformly spaced. So there is a series of points. And then let's say we had rays of light, which we're going to come into here and form an image. And let's say we had an image plane right here. And these are both right angles. These are both 90-degree angles. And that image plane forms. And for simplicity, I'll just do ray tracing, rays of valence flux, metavision as we call it, which is this metavalence flux that comes out of the camera, like this. And so we see what happens is that each ray of light that enters the camera, or each ray of darkness that exits the camera, passes through the image plane accordingly. So on. Don't need to draw all of them, but you can get the general idea. And so this is big Z here, this distance. And this is little z here, this distance. And then right here, this is little. So we'll pick some point, pick some arbitrary point, say in blue here, this point P, off in the blue yonder, big P. And big P maps to little p, much closer to us inside the image plane. And big X is the variable. So within this camera configuration, big Z and little z are constants. And X is a variable that varies from pixel to pixel. If this was a pixel lattice, first pixel, second pixel, third pixel, fourth pixel, on some imaging array it could be, or it could be some structure that has periodicity in it, such as a row of bricks or railway ties or ceiling tiles or something like that. And so that we have here point P, and we might have more generally X1, or big X1, big X1, big X2, X3, and so on. And then when that gets imaged down, this goes to little x1, little x2, little x3, and so on. And so those points all map in this way, in a very simple way. And so if there's periodicity in the real world, as there often is, repeating bricks, ceiling tiles, objects that repeat, the same thing repeats over and over again, that periodicity gets mapped to periodicity here. So if we had some periodic structure in the domain of this mapping, this is called the domain, and this is called the range of the mapping. And it's a mathematical mapping from domain to range. And so there's a periodicity. If there's periodicity in the domain, it maps to periodicity in the range. So if there was a periodic structure, it would admit a Fourier series. And so we know that a periodic structure can be represented as a Fourier series. So we might have the fundamental will be a sine wave like this, and there'll be a cos wave. We can say it's complex. We can take this plus the square root of -1 times that. And I've just drawn x this way, spatially. Say x sub r for the real part, and x sub I for the imaginary part. And that's your Fourier series that represents that. And then we might have the second harmonic, which is twice the frequency for the real part, and same for the imaginary part, 3 times, 4 times, and so on, integer multiples. And then that Fourier series here gets mapped to another Fourier series over here. So we can use tools like Fourier transform or wavelet transform to analyze this image quite effectively. However, generally speaking, in the real world, as we typically see images, pictures of things and so on, the situation might more typically be this. We'll have here some subject matter. might be subject matter like this. And maybe it's a periodic pattern like a row of bricks or tiles or other objects, or just a pixel array, which is also a periodic lattice. And then coming out of that, roughly speaking, right about here, let's say. And that looks like about 90 degrees, doesn't it? And we'll have coming out of that. And here's P, or the COP, I mean, center of projection. That's coming out of that. Now typically, what we might have is the camera won't necessarily be pointing parallel to it, but it'll be pointing at some other angle oftentimes. So the camera might be taking a picture like this. So let's say this is a tall building here, and you're pointing your camera up a little bit to look at that tall building. And let's say, realistically speaking, your center of projection is there, and we get this at roughly 90 degrees. Looks about right. So here's our image plane. Now let's do the same thing here. And we'll see that it's slightly longer. Get one here. Another line here. Another line here. And one here. 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 And then I'll skip the OA, the optical axis. Here. And one here. And this one comes right down the optical axis here, so we kind of skip that one too. And then here, and here, here. Now, what do we notice here? Well, what we notice is that the lattice is no longer periodic. You see right here, what we have is that this point, if we look at this series of points here, there's a point here, another one here, another one here, another one here, another, so on. What we notice is that the points are getting closer together over here than they are over here. So they're widely spaced over here and closely spaced over here. And that's something that's called a chirp, like the sound that birds make, you know, up chirp or down chirp. Down chirp. And so it's not a steady sine wave or cos wave like. But rather it's kind of a chirping sound that goes up or down if we were to listen to it as a function of time, as an audio waveform, but it's actually a spatial phenomenology. But you can see that there's this varying frequency as we move along the space. So let us understand the mathematical relationship between domain and range, because I could ask a simple question. I could ask you to tell me what is the relationship between the domain and range under this kind of mapping. So if I said, I have a mapping like this, and the simplest way to define it is to this. We draw a line there. And then, let's take this out so it's not too confusing. And then, this is at right angles. And let me say I have a camera that's aimed this way, just like we had here. So this is the direction my camera's aimed. And then from this camera, there's a bunch of different points. We kind of have them all coming out at different angles like this. And let's just pick one of them for simplicity. And we'll call that here point P, some point P, capital P, in the real world. And there'll be various subject matter here. You might have different objects here. And point P is one of the points that's in that real world. And right here, we'll call this X1, big X1 is right here. And then let's say point P intersects. Let's draw a line that passes through point P and passes here at right angles. And that distance here, we'll call this X2, big X2. Maybe I'll write letter P over here so that it's less confusing. And so big X2 is the distance from there to there. And now we're going to take this as a camera. So we have big Z1 is this distance here. And then we have big Z2 this distance here along that optical axis. And then now we're going to take little Z1 is this distance here that we're imaging down to in the first camera. And imagine there's a second camera, which is tipped over this way, which is really just the same camera at a different point in time as we're shooting a video sequence, say. And we might swing the camera around a little bit. We can even zoom in a little bit more while we're swinging the camera. So let's say it might even have a zoom lens, and we can zoom in here a little bit. By zooming in, increasing the magnification, it just means we're moving the image plane further away from the COP so that everything's magnified just a little bit in that second frame of reference. And so you can see here that this is going to be X, little x1 is going to be here. And then you can see little x2 is this distance here. And let's suppose that the camera went through an angle theta that it panned. And let's suppose in regards to the point that we're looking at, point P, that point P, in regards to the first camera's coordinate system, has subtended an angle of alpha. So that gives us a relationship between x1 and x2. What we really want is the relationship between little x1 and little x2. We want little x2 as a function of little x1 And that will give us the relationship between these two pictures, because these two photographs of this same reality here have a relationship between them. And if we can understand the relationship between these two pictures of the same subject matter, it'll help us greatly understand how this world of imaging works. And so now we can write that tangent, start getting higher, I guess. Tangent of alpha equal little x1 over little x2, or little x1 over little z1. So tan of alpha is little x1 over little z1, or big x1 over big z1. And then now the other angle that we have is tan alpha minus theta, and that's the angle in this second camera. So this little angle here, so I'll fill that in orange here. That little angle here is alpha minus theta. And so that forms, there's a little triangle here, like this. And in that little triangle, tangent of that angle, which is alpha minus theta, is little x2 over little z2. And I'll just draw a little z2 as this distance here. And so this x2 or little z2, which is also equal to big x2 over big z2. So now what we really care about is the relationship between little x2 and little x1. And so we can write x2 equals z2 tan alpha minus theta. And we know a well-known trigonometric identity is the tangent of the difference of two angles, such as theta minus alpha, or alpha minus theta, I mean, equals tan alpha minus tan theta over 1 plus tan alpha tan theta. So using this identity here, we can see that this is just z2 times that. So we have that x2 equals z2 times this fraction, tan alpha minus tan theta over 1 plus tan alpha tan theta. Now let's introduce some variables. Let A equal Z2 over Z1. So A is a constant just equal to the zoom ratio settings. Z2 divided by Z1, which is the relative scale between the images, how much one's zoomed with respect to the other. And let B equal negative Z2 tan theta. And remember that theta is a constant for this situation. So theta is just the constant that describes the angle relationship between the two cameras. And then, of course, the variable x varies throughout the image plane. but for all pixels in the image plane at this moment in time, theta is a constant, and so tan theta is a constant, and z2 times tan theta is a constant, and negative z2 tan theta is a constant. We'll just for convenience call that b. And then we'll introduce a third constant, c, which is equal to tan theta over z1. So now we have these three variables, a, b, and c. And so now we can write simply, in a very beautiful and simple way, x2 equals ax1 plus b all over cx2 plus 1. And so now this is a relationship between the pixels in the first image and the pixels in the second image. So it gives us a mathematical relationship between where we are in this image and where we are in this image. So it tells us how two differently aimed pictures of the same subject matter are related to one another. And the way that they're related is through this numerator is an affine relationship. So if I just say the domain is x in one and the range is y in the other, you've got this very simple kind of relationship. And the y, you can plot this graph too. I could plot a graph of ax plus b over cx plus 1. A, b, and c are constants. Pick three constants, a, b, and c, and do an xy plot of this relationship here. And what you can see is that a is the scale, b is the offset. So numerator, that's an affine relationship. And in the original case, when the image plane was parallel to the object plane, or the two image planes were parallel, then that's the no chirp case. So this is scale, this is offset, and this is chirp. This is how chirpy it is. This is called chirp. That's the degree to which the frequency changes. Up chirp or down chirp. How much is it chirping? If the chirp rate is 0 and it's not chirping, the special case is that 0, and then the denominator equals 1, and then this is simply y equals ax plus b, and it's simply an offset and a scale. So that's a very simple relationship between two images of the same subject matter when we are at a fixed center of projection. So when we're doing a panorama and exploring a room to build a virtual reality environment map, we just start at one spot and swing the camera all that. Under arbitrary camera movement, the relationship's quite more complicated. But another special case is when the subject matter exists on a flat planar surface. So if you're photographing subject matter that's flat, like the face of a building or the side of a streetcar, then what you have is you've also got the same kind of relationship. And you can by y equals ax plus b over cx plus 1. And there's a little bit more to this if you read through the chapter 6 of the book, but this just gives you a general idea of, so now we can totally understand the relationship between multiple pictures of the same subject matter. Let's just switch back to my main camera and drive this point home. So let's say if I look up at my ceiling tiles there on the ceiling, let me turn this around so you can look right up at the ceiling. If my camera will keep working. So you can see, I probably got overexposure. I gotta dial this down a little bit. There, you can see the ceiling tiles, they're all the same size now in the image plane. They're all equal sized. You can't see all of them because some of them are blocked, but the ones that you can see are all the same size. And as I tip the camera down this way, what you notice is that the ceiling tiles at the top of the image, the ones up here, take up more pixels in the image. They're larger in the image plane, and the ones near the bottom take up fewer pixels. Like if you look at how many pixels that one takes up there and moves that same pixel dimension up here, this one is 4 times bigger than the one down here. And so that is a chirp. The spatial frequency is changing. So as we go from the top of the image to the bottom of the image, that's an up chirp. It starts out at low frequencies near the top, long wavelengths, which are low frequencies. And towards the bottom, it gets to shorter wavelengths, which are higher frequencies. So as you go from top to bottom, we have an up chirp. It's like, if we had it play out in time, but of course it's a function of space, not a function of time in this case. And likewise, if we swing the camera from left to right, what we see now is that towards the left side of the image, here, the tiles are really larger in the image plane, and the same size tiles, when they're towards the right-hand side of the image, appear smaller and map just smaller number of pixels or smaller image, a smaller area on the array of the image. And so in this case, from left to right in that image, we've got an up chirp as well. So it's going as we go across the image. So if you're doing machine learning on images and you're just using the Fourier transform as your preprocessor, consider using the chirplet transform to get improved performance. And so wavelets are pieces of waves, and they're no more valid than waves for things that are chirping. And chirplets are pieces of chirps. So I hope that's been fun. So tell me your thoughts. Okay. So maybe we'll stop the recording and I'll answer any questions.